Hello students, in this video I am discussing about the Pelton wheel turbine. Okay, so in this type of this is the only type of the uh, impulse type turbine of tangential flow. Okay, so this turbine is in common use. Okay, so mainly possesses a nozzle, runner and buckets, casing, brake nozzles. Okay, as you can see from the figure. Okay, so the water from the dam is made to flow over the penstock. At the end of the penstock, the nozzle is fitted, which convert the pressure, that is potential energy, into high kinetic energy. Okay, so the speed of the jet assuming from the nozzle that can be regulated by operating the spearhead. Okay, by varying the flow area. Okay, so the high velocity of the jet impinging on over the blades or a runner, due to which the runner starts rotating because of the impulse effects, uh, and thereby hydraulic energy is converted into mechanical energy. Okay, so after the runner the water falls into tail race. Okay, tail race here, and causing so casing is provided the provide the housing for a runner, which and it is open to atmosphere. Okay, so brake nozzles are used to bring the runner from the high speed to rest condition wherever it is to be stopped. Okay, so in order to achieve this, water is made to flow in opposite direction through a brake nozzle to that of runner. Okay, so next part of this Pelton wheel is head and efficiencies of the hydraulic turbine. Okay, so hydraulic heads. In case of hydraulic heads, there are two types. First one is a gross head and the effective head. Okay, so the gross head, it is the difference between the head race and the tail race level when there is no flow. Okay, so as such it as such it is termed as a static head, and it is denoted by HS or HG. Okay, so and the second one is effective head. Second one is effective head. Second, okay, effective head. It is a head available at the inlet of the turbine, and it is obtained by considering the all head losses in a penstock. Okay, if HF is the total loss, then the effective head, then HE is the effective head. Okay, so above the turbine, that is H is equals to HG minus HF. Okay, so next we move on to efficiencies. Okay, there are four efficiencies here. First one is hydraulic efficiency, volumetric efficiency, and mechanical efficiency, and overall efficiency. Okay, first one is the hydraulic efficiency. Here it is a ratio of power developed by the runner to the water power available at the inlet of the turbine. Okay, so it is given by NH is equals to H minus HF divided by H. Okay, where H is the effective head at the inlet of the turbine. Okay, so the next one is volumetric efficiency. It is the ratio of quantity of the water actually striking the runner to the quantity of water supplied to the runner. Okay, so efficiency volume is equals to q minus delta q divided by q. Okay, that is the q actual by q theoretical. So delta q is the amount of water that slips directly to the tail race. Okay, which is equals to losses. Okay, so the next one is a mechanical efficiency. It is the ratio of shaft power output by the turbine to the power developed by the runner. Okay, so it is given by efficiency mech is equals to shaft power output divided by power developed by the runner. So which is given by SP divided by rho into q into u1 vu1 plus or minus u2 vu2 divided by gc. Okay, so the last one is overall efficiency. Okay, it is a ratio of shaft output power by the turbine to the water power available at the inlet of the turbine. Okay, that is shaft power output to water power inlet. Okay, so it is given by sp divided by uh, rho q into gh. Okay, so the overall efficiency is equals to hydraulic efficiency into volumetric efficiency into mechanical efficiency. Okay, so next we move on to work done by the Pelton wheel. This is the velocity triangle for the Pelton wheel. Okay, same, this is a common for all the problems. While solving the problem, this velocity triangle remains the same. Okay, this triangle we have to use for the problems. Okay, so here as you can see, this is the nozzle where the water flows. Okay, so theta is the angle through which the jet is deflected by the bucket, that is a bucket. Okay, and beta 2 is the runner tip angle. Okay, that is 180 minus theta. So this figure shows that the inlet and outlet velocity triangles, right? So the first one is a inlet, the top one is a inlet, and the bottom one is outlet velocity triangle. Okay, so since the angle of entrance of the jet is 0, the inlet velocity triangle collapses to straight line. Okay, so the tangential component of the absolute velocity at the inlet, that is vu1 is equals to v1, and the relative velocity at the inlet, that is vr1 is equals to v1 minus u. Okay, so the efficiency of the uh, maximum efficiency of the Pelton wheel is given by 1 plus cb cos beta 2 divided by 2. Okay, so here if cb is equals to 1, where the then the above equation gives the maximum efficiency. Okay, for beta 2 is equals to 0 degree. Okay, this is about the velocity triangle of Pelton wheel. Okay, thank you.